Okay, so since there's been a little scheduling confusion, and I guess it is either right before or during lunch, depending on how you count, I'll keep this late and a little brief. So I want to, so in this conference we've seen a lot of takes on this phenomenon of universality. One speaker described it as, sort of mathematicians trying to do computer science, some sort of geometric gadgets for computing, and that was Kapovich and Bernd Sturmfels talked about kind of interpreting it a bit as hardness. So I'm going to start with something really a very, very applied and kind of down-to-earth thing for this group, but this is computer scientists trying to do computer science, and maybe we'll see some connections later. So here's a problem. And it's actually really quite well studied, and it goes by the name of matrix completion, which is perhaps not so descriptive, but I've put here low rank because it somehow will really matter. And so what's the game? So we see some sort of a partial matrix, which I'll call omega of A, where A is this unknown matrix, and omega is, I guess, meant to mean observation. This is, again, other people's notation. So what you see is you see some numbers, but you also see where they are in the matrix. So so your given data is the size of the matrix. You see some numbers and also their locations. And you're also told something else, namely...
What is the difference between colors?
So I'm trying to indicate that blue is what you've seen and gray is what you haven't seen, but these blue things, I really want you to imagine them, not that I just throw you some numbers and I say they're somewhere in a big matrix, arrange them how you like, but really somehow, in the applied literature, they call this a masking, right? So it's really like, somebody put a piece of cardboard down over the table and they cut out some holes, and that was what you saw. And then on the other side is the actual matrix A, and your task is get it back. Now, there's this rank. And maybe we'll think about it. And for this talk, it is fine to just actually imagine that these matrices are complex. I mean, applications, they will tend to be real numbers. But so I should say a little bit, because it's applied, about why do you do this anyway? And the answer is, imagine that what your matrix is, this is kind of the canonical motivation, that here you have some users and here you have some movies, and the entries are how much they like the movie. And of course, if everybody is a unique snowflake, then nothing can be learned, right? A new user comes, this user is potentially unlike all the other users, so there's no hope to even tell them what movies they might like. But if instead we say that, well, actually, the success of blockbusters means that probably there's a few prototypical types of people, 57, and most people are somehow a linear combination of that this explains the data adequately. So it's a kind of statistical assumption, and so this is where it comes from, this recommendation kind of question. So in real life, the observations tend to be also noisy in other kinds of applications. Typically, I want you to imagine sparse sets of observations, not really dense ones. So we're not completing one entry of a very gigantic matrix. And also, probably how you obtain these observations is pretty much unknown to you. Okay, so maybe let's do an example, one of my favorite examples. What about rank 1 matrices? Well, here you can actually kind of just, with your bare hands, see what is going on. So every column is a multiple of the first one. So if I have observed, say, 3 of these, I can, well, if I've observed these 3, I can just get back the 4th by equating the ratios. And what's going on here is, well, it's a rank 1 matrix. The 2 by 2 minors vanish. And the little formula that I've written just says if I have 3 entries in a 2 by 2 minor, I can get the last one. This might suggest something. And, so this problem has a really simple combinatorial structure, therefore. It's intimately related just to trees. So I associate with my observation pattern a bipartite graph in the natural way. there are vertices for rows, there are vertices for columns, and if I have an observation, I stick in the edge. And so what my little formula says is that if you have a path of length 3, you can close it. And from that, it's not too hard to see in this case that you can complete the whole thing exactly if this graph is connected. So this is now, at least for most true matrices. If it's all zeros, I might have a problem. But so this is good because what I want to say is this is essentially a combinatorial characterization of what can be filled out. And it's independent of the actual numbers that were there. It's independent of the size, right? It just depends on the rank and the observation pattern. Okay. Now, rank 1 is, however, a little bit restrictive. So maybe I'll start with, here is a kind of paradigmatic theorem for this area due to Candes and Tao from a few years ago. And let me say what it looks like. So I don't want to, I've put some words in red because I want to say this is what a typical theorem in this area is looking like. So first of all, it says something, so here's our true matrix, and it has some qualifier on it. The true matrix is something. In this case, it is incoherent. We have some assumption on the rank that it's really quite small. So I'm being loose here because they give actually a wide variety of bounds for a wide variety of sampling A, at least 3 or 4. And R can be slightly different, but if you take it to be constant, it will always be fine. And now the observations are also chosen in a very specific way, but not in a deterministic way. So their theorem says that we have to pick these observations randomly, and we have to pick them from a certain distribution, which is, it's Bernoulli, so we look at each entry, we flip a coin with some probability, and so this is the sort of the sampling rate, the edge probability, if you will. And it has a certain kind of order, and I'm putting a little disclaimer here because, again, they prove a bunch of different bounds. So you might have a kind of a polylog here, depending on which A and which, and no noise. And now the conclusion is with high probability. So their algorithm doesn't either work or not. It's extremely likely to work. They have an explicit algorithm, and it's a convex program. And it finds A. And in fact, their convex program doesn't really need to know R. It will just fail if R is not known to be small. Okay. And so something that I want to do is maybe explain a little bit why this theorem has such complicated hypotheses and conclusions, and maybe what else you can do. So this is sort of the start of where maybe friends and I looked at this. Because on the other hand, there's something about this particular matrix completion problem. So, so in his thesis, Mike Dobbins, whose name came up before in Arnaud's talk, proved the following fact, which is that polytope realizability reduces to low-rank matrix completion. And it does so without, I mean, if you look at the proof, it doesn't add any extra stabilization. So it has as much stabilization as Richter Gebert's proof would have introduced. And a corollary to this is that, in fact, if you make no restriction on the problem, matrix completion is going to be really quite difficult because you have seen some observations, but now if you try to invert this sitting above it at some very specially chosen observation patterns and numbers in them, you can see something stably equivalent to your favorite semi-algebraic set. So basically this problem is in some sense very hard. And so maybe this already tells you that some hypotheses are needed to make any real progress. Okay. But, and I just mentioned this, that this came from statistics. And in statistics, you always have some generative model lurking underneath. And the generative model coming from these universal things, well, I mean, it's a measure zero set, and it would have to be a truly horrible generative model. So for any reasonable model, you can probably get away from this, and so on some level this is a workshop about universality, but a lot of what I will say is kind of genericity is the way to go. Yes, it's sort of, it's anti-universality, but it's that universality, genericity on some level is a convenient way of thinking of things that is, for some actual applications, more convenient than NP hard versus average case or so, which is a bit more dicey and, yeah, so. And so, so this is what's really going on. So what's the deal with this small rank? I mean, it has a pretty simple interpretation using some basic algebraic geometry. So this underlying matrix, it's a point on a variety, and it's a really pretty famous variety, a determinantal variety. And why is it a variety? Why is the set of rank at most R matrices a variety? Well, I mean, it's just cut out by these minor equations. This is perhaps not the most advanced way of viewing it, but it certainly gets you there. And so the observation process is a set of coordinate projections now. So if you think of this, so really what's going on is that we have the determinantal variety, but I want to stress that in this kind of problem, it's not like a pure algebraic geometry setup where one looks at intrinsic aspects of the variety, its ideal or whatever. It lives in a certain embedding, and that is important in what follows. So these observations, they're coordinate projections. But this tells you pretty much right away that if you want to have any hope of completing this at all, right, if you don't want it to be really floppy, then it should be the case that the dimension of the image of this observation map should be somehow at least as big as the dimension of the determinantal variety. And that's why, and if you have sparse observations, then the dimension of the variety, which is this, has to be somehow about the same as the number of observations you made. This is a pretty basic fact, but it says that in sparse sampling regimes, also the rank has to be low. And you can say how low right away, make any progress. And so this is really an instance of a, I guess, a more general phenomenon, but Franz Kirai and Ryota Tomioka and me, it was not really fitting on the line, and Takeaki Uno, right? So we say that you can approach this problem using matroids, very similar in rigidity theory. So there's a sort of completion matroid, and so the fiber dimension is controlled by the rank of a matroid just involving the graph of the observations. So it's clear that permuting the rows and columns doesn't change anything either. So really this is a nice graph question. And so you can in fact check if a specific entry is completable. And notice that this is different than the typical theorem I showed you, which basically said, either I'll reconstruct the whole thing or I'll make no claim to you at all. And in fact, there are some sufficient conditions also for being uniquely completable, which are based on linear algebra. Those are not necessary for being uniquely completable. And another theorem is actually that if in fact it's finitely completable, so up to a finite number of choices, in fact, the number of these choices is a generic property as well. So those of you who know framework know that this is a bit of a hard theorem for frameworks. For matrix completion, it's quite a bit more straightforward to do, in fact. At least if you let yourself have complex matrices. For real ones, it's not in any way true. So for the next part of my story, I want to talk a little bit about this sampling rate and why they have it. So, because it's a perhaps strange thing if you're not used to it. So what I've said is that this is really a question about graphs. And just a fact is that if you have rank R, there's no hope to have a finite set of reconstructions if you don't see at least R things in every row and column. And so this is really a question about, well, does your graph have minimum degree at least R? And if you sample the way they do it, then you really cannot improve on this order right away. And why is that? Well, this is a fact from the theory of random graphs. So the degree sequence evolves in a certain way that is controlled roughly by what sort of coupon collectors. So a GMNP it's a bipartite graph with m and n vertices on each side, and p is the edge probability. And so in combinatorics, this is a very heavily and classically studied thing. Combinatorialists know an awful lot about it. And one of the things they know is for which p does minimum degree R happen. And that p is not far from this. So basically, by changing your perspective on the problem, you can now start to apply tools from other areas. And you can see, for example, that this is if you're picking your graphs like this is really sort of about the right sampling rate. In principle, actually, you could kill the C and push it to a lower order term. So, but the proof method of Candes and Tau, and essentially this is tight for their proof method. Anyway, so I want to say, well, my last couple minutes. So one thing I want to say is that, well, the question that we looked at was really how do you complete one entry? So the most modest of all the matrix completion problems. So it's a recommendation system. One user comes to me. We want to know about one movie. And so these convex methods are great, but basically they require you to read in the whole thing. They have various assumptions, and also they complete the whole thing. And so our approach is based, again, sort of more on algebraic ideas. And this is these circuit polynomials. So a theorem, due to friends and myself, is that to each circuit in this determinantal matroid, there's a circuit polynomial. So there's some polynomial in the entry corresponding to the circuit, and you can, so corollaries, you can use it to solve. And this is not unique to the determinantal matroid. So with Zvi, who's sitting right here in the audience, we have generalized this to a larger class of matroids. And it's unique, I guess, up to a constant. So in rank 1, back in my sort of favorite example, I showed you this schematic picture. But it wasn't, the fact that this cycle had length 4 was not really special. So if I made the same graph, but I had a much longer cycle, I could give the same kind of picture. And that's because this determinantal matroid for rank 1 is just the graphic matroid. It's a strange presentation of it. And so this comes to the last part of my story in some sense. So I talked about noise. And noise sort of ruins actually everything. But noise is kind of fundamental in machine learning problems also. So the convex methods didn't want us to have any noise. But also this algebraic approach doesn't really want you to have any noise either, because if you have some observations and they're not somehow minimal, there'll be any number of these circuit polynomials that will have to be satisfied, and the actual completion requires them all to line up. And so, of course, with noise, this won't happen anymore. So if you just plug in what you observed into the right form of these polynomials, things don't work. But still, so another theorem of Franz and myself is that this idea can still be made to go. So what you do is you naively start. So you take your observations and you plug them into your polynomial relations. And now you have obtained some estimates of what it might be, but they no longer agree. And then now your statistical problem to solve is find a good way of averaging these estimates in such a way that the variance is minimized. So, and here are some cool pictures. So let me describe some pictures. So what's going on? So this is rank 1. And this little red line on the diagonal, and also you can't see it, but there's another observed entry there, so this is the graph of a cycle, is what's observed. And here, these are the variances for, so it's possible to complete every entry, but not all equally well. So, and there's some intuition here because I told you already that in rank 1, the circuits in this matroid are cycles. And if there's noise at every thing that you see, it kind of propagates along the cycle. So long cycles suggest more noise, short cycles less noise. So things near the diagonal, the cycle that you would use to solve is shorter. They give you these nice blue things, and then it gets red until you get back to the cycle in the corners. But here's another story entirely. So this one, you can't even see it. It never projects well. This is an extremely sparse graph. This graph is a 3 regular expander. And 3 regular expanders are great because they have sort of the maximum number of cycles that you would expect for, asymptotically at least, for this many edges. And mostly they don't intersect too much. So if you notice that this combinatorial type, so this story about sort of moving from algebra and matroids, towards something really combinatorial. So this combinatorial type can, really drive down the error. It's a good set of observations, and you can analyze any one this way using this algorithm. And so you can see sort of which are good, which are not good. And then, so this one is much better. And so, yeah, I have a couple minutes, which is good. So some lessons here are some really applied-looking problems. Exhibit, they're sort of naturally algebraic. They can be universal. So just like in computer science, we're taught if you have some problem, maybe check if it's NP-complete, because then it tells you what to do. If you have some other kinds of problems, maybe check if it exhibits universality, because that might also tell you sort of how to restrict yourself. And also universality, genericity, so non-universal, is really nice. It's a good distinction in some sense that's useful for people who are trying to do stuff, or at least it was useful for me and my collaborators. And it sort of kills all of this average case stuff, so you can bring back kind of deterministic methods and questions. Now, there are some directions, but there are some questions that I want to ask. So, like I said, a lot of this generalizes, so some work with Zvi and other work with Franz says that this idea of coherence, in fact, has a generic interpretation too, and you can prove kind of learning bounds for coordinate projections using this coherence idea, and then back out some things about frameworks and linkages. But sort of one question that I want to sort of throw out there, and I don't know if it's a good question, and it's this. So these universal constructions, right, so universality theorems say that basically singularities of any type could appear. They are based on constructions, but the constructions themselves have very specific looking combinatorial types. So, if it's some incidence matrix arising from a polytope or a line arrangement, like point line arrangement scheme coming from something von Staudt. And on the other hand, all of these good theorems like the convex methods or what Franz and I are doing, right, they tend to be very effective on kind of randomish and pseudo-randomish looking graphs. And so the question, I don't know it's a good question because I don't really know how you would quantify this, is are there some combinatorial types where the singularities that can appear are not so horrible? Because there are some graphs that look nothing at all like the ones used to prove that a certain family is universal. And so I sort of, and maybe that there's really no, so I'm asking, is there really any randomness here, right? So de-randomize it. So stop proving theorems about random graphs and state a more useful property. And I'll leave it off that the pictures that I generated come from a software package that we just put up on the web, I think this morning. So, thanks for.
Well, my impression that this sparse matrix is connected with theory of polytopes, and we have with Sporship in beginning of 90s some papers about the neighborhoodness of polytopes when number of vertices and dimension tends to infinity together, the ratio fixed. And then the question, what's the dimension of faces, it's better to say, what's the asymptotics of the number of vertices, such that each set with this number is face. And we gave very precise asymptotics, which later was used, some people from statistics who studied just sparse matrices and solved some problem. I don't know the relation, but it's immediately remember me. And by the way, I think that in general, very interesting this kind of asymptotics problem when number of vertices or something else tends to infinity with maybe another, together with another. And to look at the asymptotics, because one of my theses is just that universality and randomness in many situations coincide. For graph, it's well known. For metric space also, but I think that's a general principle which we must try to investigate in any situation. Yeah.
So maybe we could have another word or two on this discussion of genericity for graphs. I mean, graphs, I suppose, you have various families with the structure on them. I mean, sometimes you're thinking about bipartite graphs.
Yeah.
Sometimes you're thinking, I suppose, about general graphs. Do you have any sense of sort of what sort of structural constraints you would be starting out with?
So the thing is that I don't. I mean, I think it's a completely ill-defined thing, and I'm sort of throwing it out to this crowd sort of as a way of simply asking the question that, so that all universality proofs that I know about sort of iterate local constructions, and they produce graphs that have like a pretty clear look, and so, I would sort of expect that graphs with like really good expansion properties or other sort of other complexity properties might be different, because those are actually the ones that are arising in this other kind of theorem, these upper bounds like the Kunda's tau that I showed you, or there are some theorems about frameworks that give much more precise information about the evolution of rigidity in random graphs, and all of those families are sort of very well they're mixed up and they're very complicated, and so I thought that maybe I would throw yeah.
So finite fields, we know that more real lineability is characterized by a finite number of minors, right? That's a new result currently. And so if you have a finite number of minors, then you know by the theorem of frequency, then you have a sharp threshold, right? So
Yeah.
you have a factorization actually. So you can probably say that above this threshold, you should see no universality of these like random, actually quasi-random, which theorem also has no pure, you should see the universality for a phenomena there, but I don't know whether this works for complex numbers.
Oh, that's really nice.
Thank you.
Thanks for
Very
having me.
good.